Welcome to the channel. Thanks for joining us, your one-stop for everything AI. If this is your first time, please consider subscribing and ringing that all notification bell. Go ahead and share your thoughts in the comments. We are highly interested in your feedback. Robots have become deeply integrated into modern life, from industrial manufacturing to vacuuming our homes. However, robots lack the social intelligence to interact with humans in natural and intuitive ways. Developing these capabilities are critical for assistive robots that can cooperate with people as useful partners. Simulation platforms offer a promising path for training robots to exhibit social skills. By immersing artificial agents in virtual environments alongside simulated humans, they can learn collaborative abilities like theory of mind, legible motion, spatial coordination, and verbal communication. Following massive simulation practices, these models can then be transferred to physical robots. Habitat 3.0 from Meta AI represents the cutting edge in simulation for social robotics research. By combining high-fidelity human avatars with rich interactive environments, Habitat 3.0 enables scalable training of assistive robots that can perceive, communicate with, and help people in the real world. At the center of this vision are three key innovations: Habitat 3.0, the Habitat Synthetic Scenes dataset, and the HomeRobot. Together, these provide the simulation platforms, datasets, and robot interfaces crucial for designing, training, and testing social intelligence in robots. Simulation has become a vital tool for training robots and testing AI algorithms before deployment in the real world. In simulation, robots can be trained through millions of trial and error episodes in just days rather than weeks or months with physical robots. This allows quick iteration on ideas. Testing unfinished algorithms on real robots poses risks to both the robot and its environment. Simulations provide a safe space to fix bugs. Physical platforms require expensive sensors and maintenance. Simulation is low cost, allowing access to more researchers. Simulated environments can be manipulated easily, allowing robust testing across diverse conditions. The real world lacks this control. Data collection for AI training is expensive and slow with real-world robots. Simulations enable cheap, rapid generations of massive datasets. As robot learning algorithms grow more complex, simulation becomes critical for development before real-world deployment. Meta AI's Habitat Simulator spearheads cutting-edge research in this domain. Habitat is an AI simulator focused on embodied agents. Robots situated in interactive 3D environments. Habitat allows high-fidelity simulation of sensors and robot body dynamics, while also providing semantic scene understanding for navigation and manipulation research. Functions exist for agent control and motion, and managing navigation and object interactions. These configurable 3D environments import realistic 3D indoor scenes, including object physics and mechanics. Habitat was open-sourced by Meta AI in 2019. Then Habitat hit a major milestone with Habitat 2.0 in 2020, by introducing simulation of robot manipulation capabilities, and interactive objects like drawers and doors. This expanded the scope of research from just navigation to more complex skills required in real-world environments. In 2022, Meta AI released Habitat 3.0, representing a monumental leap in simulation technology for robotics. If previous versions enabled robots to perceive and move through environments, Habitat 3.0 adds the crucial capacity to understand and interact with other agents. Habitat 3.0 introduces high-fidelity simulation of humanoid avatars, unlocking critical new research directions in human-robot interaction. Robots can now be trained alongside digital humans in collaborative tasks, developing social intelligence skills for assisting humans in the real world. This focus on human-robot interaction simulation is the logical next step for Habitat. While navigation and manipulation skills are important, truly assistive robots need to understand human partners, predict behavior, and coordinate actions. Simulations are the only viable methods to generate the massive interactions and datasets necessary. The simulator provides high-quality humanoid models, with articulated skeletons, and surface mesh skins enabling natural motion. The human models possess diverse appearance and gender representations, simulating variability in the real world. Habitat 3.0 offers several methods for controlling avatar motions and actions during simulation. Such scripted movements are generated programmatically, like walking between waypoints. Also, there is real-time control by humans via keyboard, mouse, or virtual reality interfaces. Neural network agents are trained through reinforcement learning to map states to actions. These control modes allow data generation through both scripted and avatar behavior, as well as natural human interactions. The avatars possess simulated vision sensors and can interact with objects and doors. This allows realistic embodiment and situational awareness for collaboration. Habitat 3.0 provides benchmark tasks designed to exercise collaborative human-robot skills. The robot must find and follow a human avatar through the scene, maintaining proper distance and avoiding collisions. The robot and human avatar jointly rearrange objects in a scene to tidy up, like clearing clutter in a living room. These tasks require recognizing human actions, spatial reasoning between agents, and planning coordinated motions, which are crucial skills for assistive robots. Robot policies can be trained through reinforcement learning on avatar collaboration in simulation. This enables completely autonomous robots. Human operators can control avatars and generate expert demonstration data for imitation learning approaches. Humans can be looped in to control avatars real-time. This allows sim-to-real transfer testing and calibration. Together, these modes allow developing robots that can understand and assist human partners for everyday tasks. Habitat 3.0 represents a monumental leap for robotic simulation. The platform provides the first scalable solution for training robots that exhibit social intelligence alongside humans in rich, interactive environments. This builds the core capabilities needed for real-world assistive robots. These capabilities push well beyond basic navigation and manipulation into higher-level social cognition. While extremely difficult to develop on physical robots alone, Habitat 3.0 provides the simulation framework necessary to train sophisticated models for social intelligence. Habitat 3.0 architecture comprises several key software components for enabling highly realistic, multi-agent, human-robot interaction simulations. The simulator's backend implements physics for agents, objects, and scene interactions. Also 3D component rendering, with configurable visual sensor models, and real-time interactive control, via keyboard, joystick or virtual reality. Behaviors are defined programmatically for data generation. Neural networks are also trained through simulations. Control logic can be mixed, e.g. learned policies for navigation, and playable actions for object manipulation. Agent policies use observations from sensors to determine actions. To validate Habitat 3.0 Feat's capabilities, initial case studies were conducted on the included social navigation and social rearrangement benchmarks. By training agents on these tasks, emergent social behaviors were developed. For this task, a robot must navigate scenes to follow a human avatar, avoiding collisions and maintaining appropriate space. Heuristic and learning-based methods were tested. This cooperative task involves a robot and human avatar jointly tidying up a room by moving objects to designated locations. A baseline heuristic policy was compared to a reinforcement learning trained policy. Scripted logic for finding closest objects and navigating to target locations. This demonstrates the benefits of integration training over decomposed logic. These initial experiments prove that although extremely challenging, Habitat 3.0 can successfully train robots for legible, intelligible social behavior, alongside people in collaborative tasks. Training social intelligence requires large, diverse datasets of human habitats for simulation. However, most existing interior scene datasets lack realism or diversity. To overcome this, Meta AI introduced Habitat Home, a new high-quality dataset of fully furnished home environments for Habitat 3.0. Habitat Home contains 50 unique full home layouts, with over 400 rooms. Homes exhibit a range of architectural styles, from modern apartments to ornate mansions. Each scene is populated with furniture and props, styled realistically like a lived-in home. The contents were designed by professional interior decorators, and modeled after real-world furniture catalogs, for maximum realism. Full compatibility with Habitat benchmarks. This new dataset raises the bar for visual and functional realism, and indoor simulations. When combined with the human avatars in Habitat 3.0, it provides an unparalleled platform for social AI research. Habitat provides tooling to transfer trained policies, from simulation to real robots. Habitat supports exporting trained policies, as standalone Python modules, that implement a common robot control interface. This allows running the same policy code, on both simulated, and physical robot backends. For validation on physical platforms, Habitat training policies have been tested on several research robots such as the Toyota Human Support Robot, which is an omnidirectional robot, designed for assisting humans in home and workplace environments. It features an arm with 5 degrees of freedom for manipulation. Policies trained in simulation were deployed on human support robot for tasks, like following humans and object handover. The sim-trained policies led to more smooth and compliant motions than hand-coded baselines. Boston Dynamics Spot is a quadruped robot, capable of traversing a wide range of terrain. It provides payload interfaces for mounting sensors and arms. Using Habitat policies, Spot robots were able to reliably follow humans down hallways, and avoid collisions, even when people behaved unpredictably. The UR5 from Universal Robots is a flexible industrial arm, designed for lightweight assembly and pick and place. By mounting the UR5 on a mobile base, Habitat navigation policies were used for mobile manipulation, like transporting objects, handed by a human partner. These early trials indicate that models trained in the Habitat 3.0 simulator can deploy effectively to collaborative mobile robots. Datasets generated in Habitat can train models to segment 3D scenes and detect objects from sensory inputs. This provides robots with situational awareness. Robots can learn to incrementally build semantic maps of environments by exploring simulation scenes. Using natural language interfaces, robots can learn to ground freeform voice commands into actions. Robots can learn skills by imitating human teleoperation demonstrations in simulation. Varied scenarios allow training single models to perform diverse tasks based on context, an important capability for generalist robots. Open-ended interaction in simulation provides unlimited training data for self-supervised techniques, like contrastive learning. Simulated sensing noise and physics imperfections can help bridge the reality gap when transferring policies to physical platforms. Habitat enables all these critical research directions in embodied AI, while abstracting away low-level control, allowing researchers to focus on high-level tasks. A key priority for Meta AI is promoting open research and accessibility with Habitat. Habitat is fully open source, under permissive licensing. Documentation includes dozens of interactive tutorials. Pre-built Docker containers simplify setup. Extensive Python APIs lower the barrier to use. Active developer forums provide community support. This has resulted in broad adoption. Since the initial open source release, Habitat has been integrated into over 200 research institutions and commercial organizations. Monthly downloads exceed 15,000. Developer feedback praises Habitat's extensive capabilities via simple interfaces. It has become many researchers' primary simulation tool for embodied AI projects. This widespread community validation proves the power of open ecosystems for catalyzing innovation and impact. Habitat has transformed from a promising research prototype into one of the foremost platforms driving progress in AI. Habitat 3.0 cements position at the cutting edge, with unprecedented support for social interaction research. While simulation will never fully capture all real-world complexity, Habitat provides the ideal balance of fidelity, scalability, and flexibility needed to develop socially intelligent robots. With platforms like Habitat 3.0, rapid iteration on collaborative algorithms is finally feasible. Social intelligence requires not just replicating human functionality, but also understanding human communication, norms, and mental states. This interdisciplinary research pushes AI into new territory, at the intersection of robotics, psychology, cognitive science, and more. The next few years promises exciting advancements. Habitat 3.0 crucially enables a transition from training AI in isolation to models that learn cooperatively with humans. This forces consideration of human needs and preferences in system design. While performance benchmarks are important, human-centered metrics, focused on legibility, comfort, and trust, will become increasingly prominent. Developing collaborative intelligence requires looking beyond narrow tasks and datasets. Truly assistive robots need open-ended learning, in rich environments, alongside people to absorb social practices. Habitat Home provides the necessary platform for this immersive training. Real-world evaluation should prioritize not just task success, but also human receptiveness through measures of natural motion, effective communication, and emotional influence. Habitat continues to expand into new research frontiers, like virtual reality environments, outdoor navigation, and models that reason about human ergonomics and utility when collaborating. The platform lowers barriers for academics, small companies, and students to contribute. Meta acts as a steward, investing in open tools that benefit the entire ecosystem. At its core, artificial intelligence seeks to amplify human capabilities. As AI gains social proficiency, humans remain the arbiters in how these technologies are applied for good. Open research environments, like Habitat, facilitate public discourse and involvement in shaping assistive robots in our collective best interest. The future remains uncertain, but Habitat puts it on more favorable foundations. When robots perceive, think, and act in human terms, they transition from research curiosities into allies and companions in our lives. Much work lies ahead, but Habitat 3.0 represents a transformative step to get there. Simulation platforms like Habitat are foundational for developing artificial intelligence that exhibits social common sense. Thorough testing in virtual environments allows safe, fast iteration to instill robots with social collaboration skills. Habitat 3.0 fusion of high-fidelity human avatars, detailed scene environments, and interactive benchmarks provides an unprecedented training ground for social robot intelligence research. Using Habitat assistive robots can finally acquire and refine abilities like theory of mind, legible motion, verbal communication, and cooperative planning. Alongside digital mock-ups of the people they will serve one day. Challenges remain in bridging simulation to physical robot deployment. But the power of Habitat is that it lowers the barriers to make progress. The ecosystem promotes open shared research to align these emerging technologies with humanistic goals. As AI becomes more socially apt, humans maintain responsibility in directing its use wisely. With Habitat democratizing development of assistive robots, the future looks brighter for harnessing artificial intelligence's positive potential. Simulation tools like Habitat 3.0 provide the essential infrastructure for the next evolution of artificial intelligence social robotics. By training intelligences rooted in human collaboration and assistive goals, rather than isolation and pure task performance, platforms like Habitat will help shape the future landscape of AI for societal good. In conclusion, challenges remain in making simulation to reality transfer robust. But the power of Habitat is opening up development of socially intelligent robots to more researchers across academia and industry. Democratizing innovation will lead to safer, more humanistic robots that are assisting us. Habitat 3.0 represents a transformative leap towards artificial intelligence, designed to cooperatively enhance human capabilities, rather than replace them. That is a wrap on today's video. Thank you for watching. Until next time, stay curious, stay passionate, and most importantly, stay awesome. This is Make Money AI signing off. Don't forget to click the notification bell so you never miss out on the newest updates in the world of AI. Remember, every like, comment, and share brings us closer together as a community.